Hi, I'm Si Ben-Yaakov. This presentation is entitled Difficulty in Estimating Silicon MOSFET Turn-On Losses. Let me say a few words about the background. Now, conduction and switching losses are traditionally estimated analytically by solving a set of equations. Unfortunately, however, the parameters needed to solve the equation are poorly known, not only because they are not given for our operating point in the datasheet, but also because some information is actually missing. So an example of the difficulty is illustrated in this video by considering the case of a silicon MOSFET turn-on loss case. So here I'm showing a half bridge which could represent a synchronous buck converter or say half bridge of an inverter, and I'm considering a situation in which I am in the dead time. Current is coming out of the midpoint, current is then flowing through the diode, and we are about to turn on the upper transistor, and this will be hard switching. So now we turn on the transistor and current is starting to flow here, reducing actually the current of the diode until the point that the current is equal to the inductor current and the diode current is zero, and then there is a commutation here of the voltage between the low level to the high level, which means that the voltage of the transistor across the upper side of the high level transistor is going from the full voltage to about zero when the transistor is conducting. This is, however, neglecting the reverse recovery, because if we consider it, then after the diode reaches zero current, then the current is actually reversing, so it's extending the time until the process of the reverse recovery is finished, and then there is the commutation. So here is how Texas Instruments is suggesting to deal with this process. What they are showing here is the charge of the gate, and this is the voltage of the gate, and here we see that the current of the transistor is starting to rise, and this is when the voltage will reach the threshold, the gate. Only then there starts to be a current, and then the current goes up until it reaches the inductor current, and then we have actually a linear region at which the transistor is in, and due to the Miller effect we have the plateau. And only then, when the voltage goes down to zero, we are at the on state. So the rise time of the current is from the time that the voltage reaches the threshold until we reach the plateau. Now this time is not given in the datasheet. So you need it, of course, in order to get the estimate of the total loss, which is the product of the voltage times the current. So here we have a high voltage, we have the current, and this time, as I've said, is unknown. So Texas Instruments is suggesting to estimate this time, which is this time, based on the classical MOSFET model relating the current of the drain to the voltage of the gate, and this is a second order equation, which is part of the MOSFET model. So what is missing here is this coefficient, because we know the threshold from the datasheet. Okay, we can look at it up. So what TI is suggesting to do is to look up the output characteristic of the MOSFET, here it is, and then pick up two gate voltages like 5 and 6, look at the current. So we have 2 points for this equation, and from these two equations with the 2 points we can actually extract this coefficient. Now usually the output characteristic of a MOSFET is given for a limited voltage. So if you are working at a higher voltage, which you would, this is very low voltage, you don't have this information. So you estimate it from here, and this is like an estimate. Again, you read it out from this curve. This is not a very accurate way to estimate the time. But not only that, this procedure neglects the reverse recovery. Now, since we have a reverse recovery, this is actually extending the time in which the voltage across the transistor is still the full voltage. So there's an extra time here. This is not the correct time. We have an extra time here, actually up to here, in which the voltage of the transistor is still high, and only then we have this drop. So this is not taken into account. So let me just summarize that, well, it's an estimate, it's first order, but it's not a very good estimate. Now, Infineon is also considering this situation and suggesting a way to handle it. So this is from a document entitled MOSFET Power Losses Calculation using the datasheet parameters. And here we see the same thing. We see the rise of the current. We see the voltage which start to drop when we reach this point. Now, again, this is unknown. So what Infineon is saying, well, you need this time, so you can read it from the MOSFET datasheet as shown in figure 7, and they are showing this figure 7, which is a copy of a part of a datasheet. And here indeed it says rise time 54 nanoseconds. However, this rise time is not for the current. In datasheet of silicon MOSFET, the rise time given is for the voltage. This is this part here, not the current. So I don't understand how they can refer us to this number, which is actually irrelevant to the rise. So I think this example shows that indeed there are missing parameters. In this particular case, there's a missing parameters, but all other parameters which are given for a given operating point, which in generally is not the operating point that one is interested in. So I think that at this day and age, simulation is really a much better approach. And I'm showing here an example. Here is a half bridge. Actually, these are two transistors by Infineon. And also I've added already here a thermal network that will actually generate the temperature of the junction. And this is by looking at the total power loss of the transistor, which is the product of the voltage times the current. And this goes into this network, which represents the thermal model of the transistor itself. Here is the case, and I'm assuming here that the case is 0. So what I'm seeing here is just temperature above the case. Now the modulation used in this simulation is the space vector PWM modulation. And here is the midpoint. I'm filtering it out a little bit. And here is the result of the simulation. This is the filtered midpoint, typical of a space vector modulation. Now the red is actually the loss across the transistor, the power loss. The high peaks are due to the fact that it takes into account the reverse recovery. And then the green one is the actual temperature, or the estimate of the junction temperature of the transistor. This is a frequency of 100 Hertz. And you can see that the temperature is actually going up and down during the period. So you cannot assume that an average will give you a good number. You have to take into account that within the switching cycle, you have a variation of the junction temperature. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.